All right, there we go. Now we're gonna, okay. All right. Let's get started. So today we're gonna talk about graph theory. So we're gonna start with some basic definitions, and there's gonna be a ton of vocabulary in this chapter. If you feel overwhelmed, if you need to slow down, please let me know. This is gonna be very dense. We're gonna go through 3 sections, but they're all very packed and there's a lot of new vocabulary. But I think it's going to be pretty fun. I like graphs. I like graph theory. It's very prone to people who like to think geometrically, prone to people who like to make mental models of things. It's a really useful tool. Case in point, here we have some graph models of interest. Graph theory can be used to model all sorts of interesting situations, such as social networks. So every time you have something like Facebook, for example, they have something that's called a social graph. And that social graph is essentially a graph data structure where you have nodes corresponding to people and edges corresponding to certain relations between those people. For example, did they share? Are they friends? Did they recently interact on a post, et cetera, et cetera. You can also have computer networks, and you can represent them as graphs, which makes modeling their dynamics and communication behavior very easy. And more recently, you guys are probably very aware that we have these wonderful things called neural networks. Neural networks are also, in a sense, graphs, although it's not always very useful to think of them as graphs, but nonetheless, they induce what is called a computation graph, which I'm sure I'll mention at some point in recitation or during this one or the next one. And the computation graph essentially determines how the execution of the mathematical operations that are in the network will play out on your computer. There's different kinds of graphs, as you can see from their structure. A neural network specifically is what is called a directed acyclic graph, because the edges are directed. They have arrows and they flow in one direction, and there's no cycles. There's different kinds of graphs. We're going to learn some of these vocabulary, and we're going to do a bunch of theorems, proofs, definitions, etc. So let's start to formalize things a little bit. What is a graph? So a graph is a tuple of sets. So a graph G, and let me get my laser pointer here. Pen and laser pointer too, okay. So a graph G consists of a finite non-empty set V of objects called vertices and a set of edges, links or lines, E of 2-element subsets of V. So V is going to be a set of things, and E is going to be a set of 2-element subsets of V, of tuples. The set V is called the vertex set of G, while E is called the edge set of G. And we can refer to them as V of G or E of G, respectively. So for example, here we have a graphical representation of a graph. We have a bunch of vertices, B1 for B5, and we have a bunch of edges. And look at the edges, they're sort of tuples. So each element of this edge set is a combination of 2 elements of the vertex set. So V1, V2 would be an edge, which corresponds to this edge here, for example. So for some reason I'm having trouble with the arrows. Oh, it's because of zoom. Okay. If X or Y, or alternatively the tuple XY, you can choose how to represent it, both are perfectly fine, consists of an edge in E, then we say that X and Y are adjacent, okay? So for example, V1 and V2 are adjacent because they share an edge. This is vocabulary. So a vertex that is adjacent to X, it's called a neighbor of X because they're adjacent, they're close together, right? They're connected. And the set of neighbors of X is called the neighborhood of X, denoted by N of X. For example, here we have that B1 is a neighbor of V2, and the neighborhood of V2 is V1, V3, and B4, because V1 is connected, B3 is connected, B4 is connected. They're all connected to V2. They're all adjacent to V2. Okay. Lastly, we say that the edge XY is incident with X and incident with Y, because they're neighbors. And this is the edge that connects those neighbors. So incident is a word about edges. That's the important part. Okay, so let's see some examples. A representative of a company finds it convenient to travel to 8 cities, denoted C1 for C8. Her favorite airline has direct routes between various pairs of these cities. In particular, there are direct routes from C1 to C3, C4, C7, and back again, which we denote by C1, C3, C4, C7 in this manner. This is what we will call an adjacency set, or adjacency. We can make an adjacency list. We're going to see some representations soon. The complete set of routes is given below. So this specifies a graph. This says C1 is related to C3, C4, C7. Now, every time you model something as a graph, you need to ask yourself, what are the vertices and what are the edges? So in this case, the vertices will be cities, and the edges will be whether there exists a direct flight between those cities. So then we can model the graph in this manner. So if you see here, C1 is related to C3, C4, and C7. So C7 is here, C4, and C3. And so you do it like this. Now, this is a question, and I want someone to answer. Is the answer unique? So that means if I draw this picture, and I draw this picture, does this work? Well, the answer is not unique. The answer is not unique because we can permute the labels, and we can also choose where to place the vertices. What is important is that the adjacency structure of the graph is the same, that everything is related to everything. Now, in this case, this one does not work, even though it's the same rotated structure, only because the labels are permuted in a way that the correspondence is lost. So this one does not work. But if we were to rotate this and not change these labels, then it would work. Now, this is just a hint of an intuition that we're going to develop soon, which is called an isomorphism. But just keep in mind that the way in which we draw the graph doesn't matter, but the labels of the graph need to correspond to the way in which we model the situation. So let's have another example. 5 graduating seniors, Avery, Venton, Casey, Don, and Edwin, have learned of 6 positions available in an appliance company, a bank, a chemical company, a defense company, an electronics company, and a financial institution. The students decide to apply for these positions as listed below. And here we have the specification. So we can model the situation by means of a graph where the students are A, B, C, D, E, and the jobs are A, B, C, D, E, F, lowercase, respectively. And luckily, like all of these have they start with the right letter, right? So it's pretty easy to model with these letters. Again, we can model a situation fairly easily. We do it like this. And notice that this graph has an interesting structure in which there's no connection between these nodes, and there's no connection between these nodes at the top. They're only connected. The top ones are connected to the bottom ones and vice versa, but not across. This is a specific structure of interest, and you can imagine that there are many situations that will lend themselves to this type of graph, this subclass of graph. Okay. Another one. A student is studying a divisibility of integers from the set v, 2, 3, 4, 6, 8, 9, 12, 18, 27, and is interested in those pairs of distinct integers for which one of the integers divides the other. Model this situation by a graph. So in this case, we model the situation by representing the nodes are the integers, and then we draw an edge between them, whether there exists one divides the other. Doesn't matter which. Now, technically, we could make this a directed graph if we wanted to, because divided by is not a symmetric relationship. So we could, for example, have and say, oh, no, the other way around. So we would say 4 is divisible by 2. Okay, or you could say 2 is a factor of 4, and in which case it wouldn't be an undirected graph, you would have arrows. But in this chapter, we'll mostly focus on undirected graphs. Just mentioning that so that you know that there exist other types of graphs, namely directed graphs. So some more vocabulary. The number of vertices in a graph G is called the order n of G. Typically, we reserve the letter n for the order, although you don't have to. You just need to make sure that you know what n is. So in this case, in this picture, the order is 5 because we have 5 vertices. The number of edges is called the size M of G. And in this case, we have 4 edges. So M equals 4. Now, if G contains exactly 1 vertex, then we call it a trivial graph. Non-trivial graph, what would it be? It would be a graph that has more than 1 vertex. If it has no vertices, then it's not a graph. If G has no edges, then it is called an empty graph. So again, what is non-empty? It means that it has 1 or more edges. The degree of a vertex x, denoted by degree of x, is the number of neighbors of x. So you can think of it as the cardinality of the neighbor set. So for example, B3 has a degree of 2 because it has 2 neighbors, V2 and V4. In the case of multigraphs, we actually define it as the number of incident edges because you can have multiple edges going to the same node. We haven't talked about multigraphs yet. We're going to get there in section 12.3. But a multigraph is essentially allowing us to have multiple edges between nodes, as in some of the modeling scenarios in the beginning slides. Okay, now I need to. Okay. So far, so good, guys. I know it's a lot of vocabulary. We're going to be using it over and over, so it's going to get familiar soon. Okay. So we have different ways to represent a graph, and all of them are useful in some way or another. The first one is a graphical representation, which is a picture. The difficult part about dealing with graphical representations is that we can imagine, visualize them in our heads for pretty small graphs and pretty simple graphs, but the moment we have more complicated structures, then the graphical representation ceases to be useful. In computers, for example, we might want to represent them as adjacency lists, which is similar to what we saw before, in which we specify what each node is, how each node relates to other nodes in this manner. And then another way to do that, to do the same thing, is via an adjacency matrix. So an adjacency matrix is just a we'll call a 0-1 matrix. I like to call it a binary matrix, but technically we call it a 0-1 matrix. And a 0-1 matrix is just a matrix that has either 0 or 1 in its entries. Specifically, in order to represent a graph, you will just consider it in this manner. You consider like each row and each column has an index corresponding to one of these ordered graph nodes. And then you will put a 1 whether there's an edge between those nodes. So for example, there's an edge between V1 and V2. So that is V1 is the first row, V2 is the second column. So I'm going to put a 1 there. And notice that for the case of undirected graphs, this will always be symmetric. So just like there's an edge going from V1 to V2, you can think of it as an edge going from V2 to V1 because there's no direction. So we need to put the other, we need to put a 1 also in the second row corresponding to V2, and the first column corresponding to V1. So this representation is useful because you can, for example, do a sum reduce along the columns. You can sum the rows. You can sum the entries along the rows, and that will give you the degree, right? Because if for every element that is a neighbor of let's say V3, I'm going to put a 1 in the third row, then I just need to sum the amount of 1s that I added. So this might seem trivial, but it is actually pretty useful because we can do array-based computations really fast on computers. So we might have like a very large graph, and then we can calculate the degrees of each vertex in the graph very quickly in parallel by doing a single instruction multiple data instruction on your CPU, and it's accelerated. It goes really fast because it all takes place at once, each row. So alternative representations, we also notice, again, as I said, that it's symmetric for directed graphs. So here we have symmetric matrix is a matrix that is equal to its transpose. So if we were to transpose and make the rows become the columns, then we would get the same matrix. But this is only for undirected graphs. Okay, so now we can finally start talking about some theorems. And the first theorem is quite literally called the first theorem of graph theory. Usually when you have one of these theorems called the first theorem of blah, 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 it's a theorem that might seem pretty basic, but that it nonetheless finds its way in a lot of useful applications and a lot of useful proofs as well. So this one says that, remember that the degree of a vertex is the number of neighbors. So the first theorem of graph theory says, if G is a graph of order n and size m with the following vertices, then if we were to sum the degrees of all the vertices, we will get 2 times m, where again, m is the size, m is the number of edges. Can someone like give me a quick intuition as to why that's true in the chat or unmute? Double counted, exactly right. Yeah, exactly right, Eugene. So here we have the proof. When the degrees of vertices of G are summed, each edge of G is counted twice, one for each of its 2 incident vertices. And we actually saw this in the picture that I drew. Here we have an edge between V1 and V2, and we can count how many ones we're adding to the matrix, right? We're adding 2 ones to the matrix for each edge. So remember, the degree of each vertex would just be the sum along the row. And then this quantity here, the sum of the degrees, would be, once we calculate the sum along the row, we take the sum of those numbers. So for example, 1, 3, 2, 2, 0 will be the degrees of this thing. And then if we want to calculate this, we just sum these guys. But every time I added an edge, I added 2 ones. So I contributed 1 here and 1 here. So it's pretty intuitive stuff. It might take a little bit to see how this is important. We're gonna have some proofs, but definitely you can use it readily to solve equations. For example, suppose we have a certain graph G of order n and size m equals 17. And it has one vertex of degree 1, 2 vertices of degree 2, 1 vertex of degree 3, and 2 vertices of degree 5. Then the remaining vertices of G, we also say that they have degree 4. This is just a graph. We can't see it, but we're given this information about the graph. And then we're asked, can you give me the order n? Okay, so we know that m is 17. So that immediately tells us that the sum of the degrees must be 2 times m, so 34. So now we need to make sure, now we're missing the order n. We know that the sum of the degrees, and we have a bunch of vertices here, and we're told what degree of each vertex is. So we're not told the amount of all of the vertices of degree 4, but we know that the rest of them, the ones that are not accounted in this description, are the ones that have degree 4. So then if we have 1 that has degree 1, 2 that has degree 2, 1 of degree 3, and 2 of degree 5, if the rest have degree 4, then we can count how many of degree 4 we have in terms of n. So we subtract the counts, the numbers in red, from n, and then we obtain the number of vertices that have degree 4, which will be n minus 6. So we subtract all those numbers. So now we know how many vertices will have degree 4. And then it's just a matter of unraveling this summation here using the numbers that were given, plus our unknown. So we have that 1 times 1, because we have 1 vertex of degree 1, 2 vertices of degree 2, 1 vertex of degree 3, and n minus 6 vertices of degree 4, and then also 2 vertices of degree 5. So this is just a linear equation with one unknown. We can solve for n, we obtain n equals 10, unless I did my math incorrectly. It's totally a possibility. Okay, so I just want to go through some rapid fire linear algebra because I know that not everyone here has taken linear algebra and differential equations, or whatever the CS equivalent of that is. I forgot the name. So remember that a matrix is a rectangular array of numbers. We say that it has m rows and n columns. if it has m rows and n columns, we say that it's an m by n matrix. So the first number is the number of rows every time. We call this two numbers the size of A, and if they match, then A is what we call a square matrix. Now, typically, if we have the element in row I and column J of A, we call this the ij entry of A, and we denote it by small a. So we denote matrices with boldface, and whenever I make a document, I will denote a matrix with a boldface capital letter. But its elements, when we access an element, we want to access the ij element, we denote it with lowercase and non-boldface. Okay, so here we have a few examples, 2x3 matrix like this. And if every entry is 0, 1, as we saw in the case in the graph representation, we call it a 0, 1 matrix. Now, we can add matrices together by doing an element-wise addition of the elements. In order to do this, then they must have the same shape. You cannot have two different. It's like the rectangles need to like line up. If you have different shapes, then the sum operation is undefined. So for example, if we want to add these two matrices, then we proceed element-wise. So in the new matrix, the first column, first row element is going to be the sum of the first row, first column element of the first matrix and the second matrix. I know this might seem a little bit trivial. I just don't know what kind of prerequisites you guys have, or how long ago you saw linear algebra, if you saw it in high school. I do suggest that you at least review matrix multiplication, which will be relevant for this part. Case in point, we're going to talk about matrix multiplication. You can calculate the dot product between two vectors by, and I don't like how the book defines this, to be honest, because they say that the two matrices that you multiply to get the dot product or inner product needs to be like one of them is a row and the other is a column, and then if you carry out matrix multiplication, if you carry out this operation this way, you get this. Now, I like to think of dot product as defined for arbitrary skinny vectors, whether they're rows or vectors or column vectors. In fact, typically when you talk about dot product, they have the exact same shape. But here they introduce the inner product as a way to then talk about matrix multiplication. So the inner product between two vectors or skinny matrices is just the sum reduction of their element-wise products. So if we have A1 through AN and B1 through BN, they need to be the same shape, the same length, rather. You just multiply A1 with B1, A2 with B2, and so on, and then you sum up all those entries. So you can summarize with this formula. So then this is how you define matrix multiplication. If you have two matrices, A and B, and this is the important part, their shapes, they cannot be any arbitrary shape. If they're the same shape, then you can multiply them just fine. But the important part is that when you have the matrix A that goes on the left and the matrix B that goes on the right, when you have the product AB, because matrix multiplication is not necessarily commutative, the columns of A must match the rows of B. And then you grab the columns of B and the rows of A, and that will give you the shape of the new matrix. So for example, this could be a matrix in R M by P. Again, for some of you, this is review. For some of you, hopefully none of you, this is new. But we're going to use matrix multiplication in this class, so this is the only important part that you should review. So here we have an example of matrix multiplication. I think it is not necessary to go over it. How many people want me to go over this? Anyone in the chat? No? Okay. There's one thing that is important, which is, and you might not have seen before, and that is matrix powers. So just like we can take like 2 to the power 3, we can take a matrix A to some power. Like A to the 1 would be just A. And then if we have A to the kth power, then we just multiply A by itself k times. We have k factors. Okay. So again, here we can illustrate matrix multiplication. If we have A times A, then we take the first row of A, multiply it, do dot product with the first column of A. This is 1 times 1, that's 1. 2 times 1, that's 2. 1 plus 2, that's 3. You put that element there. You proceed that way. And then you can calculate more and more and more. So this is important for one reason that we care about. And that is the fact that that we can use this to count paths. So we're going to see how to count paths in a minute. All right, more theory, more names, more definitions, more things like this. We also can have, just like we can have sets and subsets, naturally, since graphs are comprised of sets, it's natural to ask, okay, what happens if I take subsets of the edge or vertex sets? Well, the answer is that if you have a graph H, you can have a subgraph, a graph G, you can have a subgraph of G, H, such that the vertices of H are a subset of the vertices of G, and the edges of H are a subset of the edges of G. And if H is a subgraph of G and is not equal to G, then we call it a proper subgraph. In the same way that if you have a set, two sets, one is a subset of the other, and they're not equal, then we say it's a proper subset. So a subgraph H of G is said to be a spanning subgraph of G if they also have the same vertices. Okay, so here we have some examples. If I have my graph G and I remove this edge, right, I get a strictly smaller edge set like this, and I get this graph. Now, this is actually a spanning subgraph because we have all the same vertices. This is a case of a proper subgraph where that is also where we take away both edges. So we take away both edges and vertices. And the same goes here. We take away both edges and vertices. Another important vocab is complete. So a graph is complete if every two distinct vertices are adjacent. A complete graph of order n is denoted by k sub n. The graph k sub n is n minus 1 regular, and its size is n choose 2. So complete graphs just basically kind of look like this. It's like every node is connected to every other node. It's like a densely connected graph. Mostly, this is something that we use just to set up a problem. Typically, we don't use this in proofs. Now, this is a very important concept, and that is the complement of the graph. So the complement of the graph of G, and we call it G var, with the same vertices as G. So this is what it's saying, right? It's saying like the vertex set of G is the same as the vertex set of G var. So they have the same vertices, so different graph with the same vertices, such that two distinct vertices U and V of G are adjacent in G complement if and only if, or G var, if and only if U and V are not adjacent in G. Thus, if G is a graph of order n and size m, then the order of G var is n and the size of G var is n choose 2 minus m. The empty graph is of order n is therefore the complement of the regular graph k sub n, because we just saw that a k sub n denotes like the complete graph. I guess if it's not clear by now, I'm going to ask you questions. First, why is it called a complement? And second of all, since we come from a combinatorics test, can anyone tell me what this is counting? Specifically, what is this? So someone sent a direct message, ways you can combine edges. Yeah, so kind of. So the n choose 2 is the number of ways, given a vertex set, how many possible edges, how many possible edges between those vertices can you have? Because imagine, like if I have 5 vertices, n choose 2 would count the way in which I can grab 2 of these guys. And if I grab 2 of these guys, I can draw an edge. And then Koa says all the possible edges are not in the graph exactly when we take out the m, right? Because m is the number of edges in the graph. So these are all the possible edges that are not in the graph. Good job, guys. Okay, so this can give you, and then Yihan says G union G bar is complete. Yes, that is why it's called a complement. Exactly right. So if we take their edge union, it makes a complete graph. So here we can see that if we take G and we take G bar and we like superimpose them, we get, first of all, a pretty cool looking graph, but also a graph that is clearly complete, in which every vertex is connected to every other vertex. So hopefully your brain machinations are start kind of understanding that this is probably a pretty important concept. Okay. More words. So a graph of order n is a path if the vertices of G can be labeled so that the vertex set labeled in this manner and the edge set is labeled in this manner. So this convention might take a little bit to get used to, but essentially it just means that you can like index the letters corresponding to the vertices in such a way that you have V1, if you have V1 and V2, then V1, V2 is the edge connecting those, and those kind of make a path like this. So these are graphs that correspond to paths. So right now we're talking about graphs that we call paths, but there's a different notion of a path in a graph that we're going to get to when we get to 12.3. Okay, so these are all examples of paths. This is the path of 1 element, the path of 2 elements, the path of 3 elements, path of 4 elements. And these are the only paths that you can have with like 4 elements. Everything else that you could think that is a path graph with 4 elements would just essentially be a different picture, but it would be the same graph, right? Like I can have this, right? And this is the same graph as this because of that notion that we said earlier that it doesn't matter how we draw it. What really matters is that the vertices and the adjacency structure map to each other in both graphs, and then we consider them the same. We're going to see that in just a moment in a little bit more rigor. Okay. So then we also have this concept of a cycle graph, and that is pretty much what it sounds like. It is a graph that kind of forms this cycle, and we say that it has an order. So for example, the cycle of order 3 would correspond to a triangle. And then we have this notion of a regular graph. So a graph G is regular if every vertex of G has the same degree. So remember, the degree is the number of neighbors of the vertex. And we call this graph R regular if the degree happens to be R. So for example, here we have a zero regular graph because none of the vertices have any neighbors, and they all have the same number of neighbors, namely none. Here we have a two regular graph because every vertex has 2 neighbors. And here we have a 4 regular graph. So there's an intuition that can be had here. How could you go about proving that a graph G is regular if and only if its complement is regular? Like, what kind of mental picture does this provide? Does this give you guys? Try to visualize it for a second. Why is this true? Why is this true? Well, let's see. If I have this thing and I want to find its complement would be like I connect these two, and then I connect these two, and then I connect these two, and then I connect these two, wait, yeah, I connect these two, etc. So then clearly I'm going to have each node connect to like n minus r minus 1 nodes in the complement. You can see this picture here, how these form. And I just realized tragically, this kind of looks like a very creepy pentagram. But nonetheless, you can see here that yeah, this is 4 regular. What are we summoning? Mathematical demon. So this is 2 regular, and maybe we're summoning back the emoji back from the dead. And here we have the 5 vertices, and this is like, again, these 2 are complementary, right? So this is clear. Okay. Isomorphisms, and this is kind of like the big enchilada of the chapter. Isomorphism is a concept that is very broad. It's not just in graph theory. And in general, an isomorphism in math is, and even in philosophy, people use isomorphisms too, is a one-to-one corresponding or mapping between 2 sets that preserves binary relationships between elements of those sets. Those binary relationships can be many things. But in the case of graphs, 2 graphs are set, G and H are said to be the same graph if they have the same structure. We already discussed that, right? We don't care about how we draw the picture. We just care that we have the same structure between the pictures. So as we've seen, the same graph can be drawn or labeled differently, but the underlying structure remains the same. And then we say that these graphs are isomorphic. So there's a formal definition, which is it's very much worth going over. And we say that a graph G is isomorphic to a graph H, and we write it in this way with this equal with like tilde at the top button. If there exists a bijective function, and we can call it phi, that maps the vertices of G to the vertices of H. So it's a correspondence. Think about a function. Function is a correspondence, and this is a one-to-one bijective correspondence between vertices, such that 2 vertices, so if we have 2 vertices U and V that are adjacent in G, then if and only if this mapping will maintain that. It says such that 2 vertices U and V are adjacent in G if and only if, after applying the mapping, after applying phi to U and phi to V, they're still adjacent in the new codomain. So in the output map, the output graph maintains that adjacency structure. We're going to see a lot of examples, but it's essentially saying, hey, I got 2 graphs. Can I match the vertices of these 2 graphs in such a way that if two vertices were adjacent in one graph, after the mapping, their corresponding vertices are also adjacent? That's the main idea. So again, note the emphasis on adjacency, 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 adjacency. And also an isomorphism is a bijection. So one way to think about 2 isomorphic graphs is that they have the same adjacency structure. So we're going to see a ton of examples of this in recitation. And it's actually quite fun, I think, to find isomorphisms between graphs. I kind of think that even it could be something that you can have like the normies do on like the Sunday newspaper, to be honest. So, and this is also important because as we saw with paths, we had like, if we have a bunch of paths, then like if I have a path of length 4, there's only one path graph of length 4, right? And the same is true for like, generally for each order n, we have a finite number of possible graphs, and everything else is just isomorphic to one of those. So for example, we have all the graphs of order 1. Well, that's just one type of graph, right? It's just the single vertex. What about all the graphs of order 2? Well, we have 2 nodes that are either connected or not. Okay, what about all the graphs of order 3? Well, now we have a bunch of options. We can have all the nodes completely disconnected. We can have 1 node connected, 2 nodes connected, or 3 nodes connected. Notice like this is like more like combinations and not permutations, right? Because we count these, but we don't count this in here. Because if I drew this, this is isomorphic to this. It's just the same thing, but rotated. It's the same structure. And the same with order 4 and so on and so on. You get the picture. So we also know that the graphs G and H, if we have these two graphs, G and H, we can see that they're isomorphic. And again, an isomorphism is a mapping. So when you are asked to find an isomorphism, technically you're asked to find a function. Now, how you choose to represent that function, we don't really care. Like you can use a table or you can list them out like this. It's all the same. But what this is saying is that, hey, the vertex U1 in G, which is this guy, gets mapped to Y2 in H right here. You see? Now, the nice thing about graphs, about isomorphisms, is that, again, the entire adjacency structure is maintained, right? So you can immediately see that if you have this triangle here, then the vertices in this triangle must correspond to those. Now, in this case, we can choose we have two different ways of finding correspondence. There's two different ways of finding a corresponding. And then, for example, this is like a lone node. This is a degree 1 node. So therefore, it must be matched to the degree 1 node that is connected to Y2, this guy and this guy. So you can already see that it's kind of fun. It's like you're grabbing this graph, the graph on the left, and you have to find how it is like warped and transformed in such a way that the edges are preserved in order to get to the one on the right. Now, because the adjacency structure is maintained, we know a lot of things need to remain the same. So if G and H are isomorphic graphs, then we know for a fact that they have the same order, right? And that is because it's a bijection. It's a bijection, right? So this is why it's true, because it's a bijection. We cannot have a bijection that has the domain and the codomain have different cardinalities. The same for the same size. Well, actually, that's more like that's more about the isomorphism part. And then the degrees of the vertices of G are the same as the degrees of the vertices of H. So if you were to write out all of the degrees, you're going to get a list of degrees. That list of degrees needs to be the same as the list of degrees in the other graph that is isomorphic to it, up to permutation of the list. So, for example, are these two graphs isomorphic? So, first thing you want to do is actually apply this theorem, because these tell you it's basically a checklist. You check for all these conditions, and if one of these fails, then you know for a fact that the graph is not isomorphic, right? Like if I were to have one graph with 5 vertices and the other with 6 vertices, then their order is different and they cannot be isomorphisms or isomorphic. So, so this is useful because it allows you to kind of quickly rule out or to figure out whether you have to do any mental work at all, because it's pretty easy stuff. So we can do it pretty quickly, and we can say, okay, so we have the same number of vertices, so they have the same order. They all have 6 vertices. They have the same number of edges. So here we have 3, 4, 5, 6, 7, 8, 9. I'm not sure if you can hear my cat. Okay, I don't know if you can hear my cat. She's having a fit, throwing a fit. And now the degrees. So let's look at the degrees. So this is degree free. 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 So then we need all of these guys to also be degree free. Degree free, degree free, degree free, degree free, degree free, degree free. Okay. So in this case, it wasn't really helpful, but this is still something that you should always do, no matter what. Well, unless you really know right away that this will fail because they look very similar. But this is always useful to kind of reason about. It's definitely something you should consider. So are they actually isomorphic? The reason is no, because again, if they're isomorphic, you would expect the adjacency structure to be maintained, for them to have the same adjacency structure, and that includes like cycles in the graph. So for example, here we have a cycle in the graph, right? A triangle. So if these two things were isomorphic, you would expect there to be a triangle between vertices here too. And even though there's a lot of triangles like this, these are triangles that are illusions from just like the crossings of the edges. There's actually no length 3 cycle in here, right? Like if you try to find, okay, well, I go here, I go here, I go here, and then I want to go back here, but there's no direct link between these two. I have to go here and then go here. All the cycles are length 4 or more. So everyone see that? Okay, now what about these two? Are these isomorphic? Try to use your mind's eye. I get a no. Any other opinions? I get a yes, and another yes, and another yes. So it turns out they are. So imagine you grab G2 and you can rotate it in your head, and then you can say, hey, I'm gonna like untangle these two, right? If I untangle these two, like if I untangle these two, now I get the same thing. Okay. Can you guys hear my cat? Yeah, I don't know what's wrong with my cat. So it's very, you guys can hear, that's great. It's very distracting for me. Okay, so let's see another example. What about these two graphs? Are they isomorphic? I get more yes. That's right, guys. Again, think about like a continuous warping that will allow you to find the correspondence. Even if you don't do that, you can very clearly see that these cycles will correspond in some way, right? You have, and you can think about it like this. So you can say, well, P2, P1 is going to be R2, and that's because there's only one length 3 cycle in each of them, and the only guy in each length 3 cycle that has degree 2 is P1 on the left and R2 on the right. So then therefore they must match up. So you can see it's pretty fun. Like you can do like a sort of like divide and conquer type thing in order to find this, to solve this puzzle. I think it's pretty cool. And then you can like kind of imagine that you can like map these and so on. So these are isomorphic. So before we move on to the next section, just some useful things for you to keep in mind. First, you can check whether all the conditions of theorem 12.15 are satisfied. And if one of them, at least one of them, is not satisfied, then it's definitely not an isomorphism. If all of the conditions are satisfied, you can proceed by inspection first. And you say, hey, can I find an edge preserving transformation or a warp that kind of aligns both graphs? So we're going to see in recitation to show you guys ways so you can do it in a way to like actually play with it on a computer, like sort of simulator. And I think that's kind of fun. You can also think about it like if you had in real life, like kind of marbles connected by like strings, so you can like move them around. just find a mental model that you find easy to play with in your head. And it may be useful to think of the respective graphs in terms of the adjacency structures, as we said. So for example, can I find cycles or circuits of the same length in both graphs? If they both contain a free cycle or triangle, then their vertices must correspond. And as you find the correspondences, as like you find, oh, this matches with that, this matches with that, then the problem becomes easier and easier. So even if you have a lot of vertices to start with, it might seem like very daunting to find the isomorphism. The more you work on it, like the simpler all the other ones become to find. So some of them appear very tricky at first, but as you start solving them, they become much easier. Okay, so that is the first PowerPoint. So that's for 12.1. Any salient questions on this before I move to 12.2? Yes, I am posting these slides. I'm not posting them right now because I need to collapse them into slides that have like all the things, because I did this like, kind of presentation animation, and I didn't like do it. I did it like per slide. So I'm gonna do that. I'm gonna post the full thing probably tomorrow. Degree equals size equals number of edges. So size is the number of edges of the whole graph. Degree is the number of incident edges of a given vertex. So we say that a vertex has degree 3 if there are 3 outgoing or incoming, if it's undirected, it doesn't matter, edges connected to that graph. Or in the case of simple graphs that are not multigraphs, that don't have multiple edges between nodes, then it's just the same as like the cardinality of the number of neighbors, of a set of neighbors of a given vertex. We're going to see more examples. We're not even quite close to done using that terminology. So if it's not there quite yet, don't worry. Okay, so let me set up the other one. Okay. All right, so now I share my screen again. Okay. Section 12.2. So there's a lot of terminology here to start with. Some of this can get pretty confusing too. So practice makes perfect here. Okay. So first we're going to talk about this notion of a walk on a graph. And a walk on a graph is like essentially what it sounds like. But there's a formal definition nonetheless, and it says a walk. Oh, I need to set up my laser pointer. A walk in a graph G is a sequence U0 for UK of vertices of G such that UI and UI plus 1 are adjacent for all of this path. So for all of the range. So we denote the sequence in this way. And this is just essentially how like we're labeling the nodes. Essentially, it's an order sequence of like vertices that happen to be adjacent one after the other. So we call this like a U0 to UK walk, where U0 is the initial vertex of W and UK is the terminal vertex of W. So every walk has a particular length, K, which is the number of edges that are traversed. If K equals 0, we call it a trivial walk because we didn't really move from the initial vertex. An edge that is repeated m times during a walk will contribute m to the walk. So it's not like if we repeat an edge throughout a walk, we'll still count that edge. We're going to see some examples, so bear that in mind. A walk whose initial and terminal vertices are distinct is called an open walk. And a close walk is a walk whose initial and terminal vertices are the same. So I think a close walk, it's just like when you end up at this place you started. That's the way you should think about it. A close walk just end up at the same place. An open walk, you don't necessarily have to. So for example, we have this graph, and let's look at some walks. Here we have walk 1, and here we go from U to Y to W and then to C. So pretty easy stuff, right? So it's just like chuk, chuk, chuk. Then you have W2. Now this one's interesting because here what we're doing is we're going back and forth between C and X. And as we said in the previous slide, just because we're going back and forth and we're not traversing other edges doesn't mean that the walk is going to be of length 1. This is going to be, in fact, a walk of length 1, 2, 3, 4. What about this one? Well, this is a trivial walk where we have no walking, right? We're just at X and we're sitting there. And then lastly, we have this walk here. And in this walk, we are going through W 2 times, right? So we start at W, and then eventually we make it back to W. So there are many ways to, there's many types of walks. And one of them is a trail. So a trail is a walk in which no edge is encountered more than once. So there's going to be a bunch of words. We have walks, trails, paths, circuits, cycles, and then the Eulerian trails, and it's going to be a bunch of words. So it's important to familiarize yourself with all these distinctions, okay? So a trail is a walk in which no edge is encountered more than once. This essentially says that once we cross an edge in the walk, we cannot cross it again. Otherwise, it's not a trail. So for example, this is a trail because at no point we are encountering the same edge more than once. So which are not trails out of these? Out of the ones we've seen in the previous example, which one is not a trail? Two and four. Exactly right. Yeah. 2 and 4 are not trails, right? Because from here, we do CX, and then we go XC. So we go CX, and then XC. We go back. And the same goes for, and then you said 4. So here we go, well, 4 is, oh, okay, so let's look at 4. So 4 is we go from W to V, and then we go from B to U, and then we go from U to W, and then from W to C, and then from C to Y. So this one's fine, right? We cross the vertex W more than once, but we didn't cross an edge more than once. So that's the distinction. It's a good question. It's definitely is a good mistake to make because it's sometimes we forget, we mix up like, oh, which one is edge, which one is vertex. So in this case, W4 is a trail because we only care about edges, right? No edge is crossed encountered more than once. So you might be wondering, okay, well, is there a corresponding type of walk that is the same, that I don't cross a vertex twice instead of an edge twice? And yeah, there's a word for that, obviously, and it's a path. So a path is a walk in which no vertex is repeated, right? So in the case of W4 is a trail, but it is not a path because we're repeating W, right? And this is an important point. So every path is a trail, but not every trail is a path. And that will be an example of that, right? And every trail is a walk, but not every walk is a trail. right? So the respective converses are not true. Okay, so far so good, guys. We understand the distinction between walks, trails, and paths. Okay, all right. Then we have this theorem. This theorem says, if a graph G contains a UV walk for vertices U and V and G, then G also contains a UV path. So what is this saying? What is this saying? So let's look at this fish over here. And let's say that we have a UY walk. We definitely have a UY walk. It's a fish. So what is the UY path here? Can someone type it in the chat? Not quite right. So yeah, so UI UI is a path, but like what is a UI path that is guaranteed? Okay, there we go. So UY is a path that is guaranteed by the existence of the fish. Because if I find a way to go from U to Y, there's definitely a way to go from U to Y without like repeating stuff. Because you can think of the fish. The fish is just this endless, it's this worthless loop. And think about what it means to not be a path. If you are not a path, then it means that you go to the same node twice. And if you go to the same node twice, it means that you have a cycle that visits that node, that starts at that node and then ends at that node. In this case, the cycle is the fish, the head of the fish. So if we have the cycle, we know that we started the node and we ended the node. We might as well just not do the cycle. So if we have a walk, we have two options. The walk doesn't have a cycle, in which case it's a path. It is a path. And the walk does have a cycle, in which case we can just cut it out and then we get a path, such as in this case. So that's kind of the intuition as to why that's true. And we can have a little bit of a rigorous proof that sort of builds on that, and it says, it goes like this. This is certainly true if U equals V, meaning that we don't move, right? So we assume, so we assume that U is not equal to V. That way we have something that actually is interesting. So among all of the walks in G that start at U and end at V, let's grab the smallest one. There's got to be a smallest one. That's guaranteed to be the case. So then we claim that this one is a path. Now, suppose that it is not true, because if it is a path, then we're done. But suppose that it is not true. It's not true. Then some vertex of G must be repeated in W, right? In this case, in our case, in our fish, it was actual like lowercase w. So then what we can do is we can make a new walk where we cut out all that part. This is what this is saying. We're saying, hey, this is like this is we're writing down the walk, and then we're cutting out that part in which we repeat. Where we start and we start like traversing and then we go back. Everything, all of this, we cut it out. So we go from here to here. We skip all of the other stuff. We make that walk, and now this is a walk whose length is less than that of W. But this is a contradiction, because we started by saying that W is the one that is shortest. So now we arrived at one that is smaller than W, and that is still a walk from U to V. So this is how you would prove it formally. And the intuition that we develop in the fish example actually gives you a way of doing that. And this is something that's nice about graph theory, is that the intuition that you can get from like these simple examples can like usually generalize pretty nicely. Okay, So let's have a circuit. What is a circuit? A circuit is a closed trail of length 3 or more. A closed trail. So remember, we had open walks and closed walks. And closed just meant that we end up where we started. So a closed trail is a trail where we end up where we started. So all that we need is that we don't repeat any edges, right? And here, this is definitely the case. We're not repeating any edges. So this is a trail, and it's also closed because we end up back at U. We start at U, we end up back at U. And then we have this notion of cycles. So a cycle is a circuit in which no vertex is repeated, except the initial vertex and that's the terminal vertex. And the length of the cycle, we call it K, and we say it's a K cycle. And a free cycle, we call it a triangle. And then we say that a cycle of even length is an even cycle. A cycle of odd length is an odd cycle. So if you look at the picture that from the previous slide, the vertex W is repeated. We cross it twice. So that immediately tells us that this cannot be a cycle. This is a circuit, but not a cycle. Every cycle is a circuit, but not every circuit is a cycle. But we can actually decompose it into two cycles. This is a cycle and this is a cycle because there's no repeated edges in each of these triangles. So if you have a triangle, that's a cycle, basically. So far, so good? Okay. So let's do some practice. Can someone find an open trail that is not a path? So open trail that is not a path, and this is where you kind of have to start doing some recall about the vocabulary, right? An open trail. What is a trail? A trail is a walk with no repeating edges. And open means that we don't end up where we started. And what is a path? A path is one that has no repeated vertices. So if it is not a path, then it has repeated vertices. So once you understand that, all that stuff, you can parse it. And then you say, okay, I want a walk where I start and I end at different places, and I don't repeat any edges, but I do repeat a node. Okay, so we have someone said here, so Y, U, Q, T, X, X, U, okay, yeah, there you go. And then you could go, and then X, U, and then you're done, right? And this is right? Because we end up at, well, okay, no, this is not right. Because we end up at U. We need to actually go a little bit more. Oh, no, this is fine. This is fine. No, this is fine. There you go. Because it is open. Yeah, that's an example. Okay, let's do another. So what about a path? Just a path. I mean, there's many. This one's pretty easy. TQ. There you go. What about a circuit that is not a cycle? And this one, someone said, Y, Q. Okay, so here again, guys, you always need to have adjacent things, right? So I cannot do YQ. I need to first do YU and then UQ. Right? So do keep that in mind. So it would be, for example, one circuit that is not a cycle could be T, Q, Q, so T, Q, U, Y, V, R, U, X, T, right? So this is not a cycle because we're repeating the U. Okay, and then a cycle, this is pretty easy. We can just do we can do this one. Okay. So it's not so bad. Okay, counting walks. So this one, this counting walks one is a theorem, and I'm actually not going to go through the proof because it's pretty long. It's actually not very intuitive. I don't think it's very useful, but you can look at it in your own time. And what this theorem says is that if you have a graph G with a vertex set V of G and an adjacency matrix A, then for each positive integer K, the number of different VI to VJ walks of length K in G if the ij entry in the matrix A to the power of K. That's a wordful. And if you're not used to matrices, this might not be too apparent immediately. So I'm going to go through an example. So if we want to count walks here, let's say we have the graph G over here, and we want to use the theorem to determine the different possible number of VI to VJ walks of length 2 and 3 for any pair. So for like, what this is saying is, for any two of these guys that you give me, doesn't matter which, I want to find all the possible paths, that the number of paths to go from those vertices. So from here to here, for example, it is clear that we have two paths. We have this path, or we have this path. And again, path means no repeated vertices, right? Because otherwise we have infinite walks, right? But we have finitely many paths in this case. An infinite walk would be like this, like here, and then you can just keep doing this as many, well, infinitely many, because you can go here and then just walk any number of times you want, and then finally find the answer, right? But we have a finite number of paths because we don't want repeated vertices. Okay, so how do we do that? We apply the theorem. And this is where matrix multiplication comes in handy and why we did that review. So here we have the adjacency matrix corresponding to this graph, and we can confirm it really quick. For example, this says that B3 is connected to V1, V2, and V4. B3 is connected to V1, B2, and V4. Okay. And then we just take repeated powers of this. So if I take repeated powers of these, now I see that there is, and this encodes all the information of all those counts, right? So let's look at this entry. This entry says, let's say this entry says that there is one path from B3 to V2, and that's exactly right. And this entry says that there are no paths between V3 and V4 that are length 2. And that's true, because to go from B3 to B4, there's only one path of length 1, not of length 2, right? Now, what about of length 3? Oh, wait, I think this one, I think I've said it wrong. Oh, no, yes, so this is from length 2. So so from B3 to V2, this is the only path of length 2. And now what about paths of length 3? So how many paths of length 3 do we have between, let's say, oh, this is walks. Was I saying paths? Damn. Sorry about that, guys. Okay, so, whoops. Okay, so walks. So how many walks of length 4 do we have here that we're not repeating this thing? So we have 4 that goes from B3 to B1. So what are those guys? So from B3 of length 3. Oh, of length 3, duh. That's the thing I was thinking. Right. So my thing about like the infinites, that would be forget about that. I for some reason I was thinking about walks. So scratch that whole part. Again, let's look at this again. So this will tell you how many, and this kind of goes to show how kind of not useful this is for like your homework and stuff. Because if I don't know it like off the top of my heart, then probably not that useful. But I will say one thing, and this is actually a very important fact, that kind of undermines what I just said, because actually it turns out that this idea of taking powers of incidence matrices is actually and literally responsible for the creation of Google. So if you go back in time, in the 90s, when Sergey Brin and whatever the other guy was called, they were both PhD students, and they were working on a graph problem. They considered the network as a graph, and they were doing this search problem as essentially a traversal on a graph. And PageRank, which is the very first Google algorithm, was quite literally a problem that used eigenvalues and eigenvectors, which is a concept from linear algebra, to understand what happens to an incidence matrix A to a power of k as the limit of k goes to infinity. And it turns out that you can find that these things stabilize to, if you have this thing normalized, it stabilizes to the eigenvectors of the matrix for a given thing or something like that. Anyway, I'm not a graph theorist, but if you are a graph theorist, if you're working with graph theory, I mean, there's documented evidence of like very nerdy people working with this stuff, creating, I don't know, the most powerful company in the history of the world. So yeah, if you want to go check that out, that's called PageRank, the original PageRank paper. It's been a while since I looked at it, since undergrad, so I don't remember the specifics, but it's there. Anyway, so this is how you calculate, this is how you can count all of these walks, and this is nice because you can count in you can compute this in parallel because this is matrix multiplication. Computers are really, really good at this. Not for extremely large graphs, but for like simple, and not for like extremely deep walks, but that's something that you can do, and it's very useful in actual in practice. Not so much for this class, but in practice it is. And you can think that this is a little bit complicated because matrix multiplication by itself, let's assume that you have n nodes. So matrix multiplication is pretty expensive. It's at least, I think it's at least n squared. And then you multiply this, you do this k times. So for very big matrices and for very long walks, doing this is kind of prohibitive. But then you can imagine why you might be interested in doing this limit of as k goes to infinity. Anyway, I don't remember all the specifics, but it's interesting nonetheless. If you want to check that out, there's connection to this class. Okay, connectedness. So now we're going to talk about connectedness. This is another important concept, and we are at 7:47. Definitely. Okay, definitely. I think I'm going to use the 2.5 hours. Sorry, guys. Okay, so we say that a graph G is connected if for every two vertices U and V, G contains a UV path. And if G contains a UV path, then we say that U and V are connected in G. That is, G is connected if every two vertices of G are connected. Okay, so I think this is pretty intuitive to understand. So here we have an example of a connected graph. Here we have an example of a disconnected graph because we have these two different components. And you can imagine that if you have a connected graph, there's always a way to make it disconnected by taking away parts from that graph, right? In the worst case, let's think about it like this. What can you say for sure about, if I give you the degrees of any graph, what can you say for sure about like the minimal number of edges that you need to take out in order to make it disconnected? I guess, okay, one. I guess I didn't frame this right. Actually, let me draw the picture. So if I have a vertex of degree 3, of degree 4, I know for a fact that if I take out all of these guys, then this guy's going to be floating by itself. So now the graph is disconnected, right? And if I if I have like, this is degree 3, this is degree 2, this is degree 4, this is degree 1, this is degree 3, this is degree 1, then I can look at like the smallest of the degrees, and then I know for a fact that that I can like go to that guy, to like the smallest degree node, and cut off all of its things and create a disconnected graph, because now this guy's going to be floating, or this guy's going to be floating. So that might come in handy for some proofs. Might. Okay, so loosely speaking, we say that the components of a graph are its connected pieces. And we have a function that counts the number of components of a graph. I mean, that's K of G. So for example, here, because G1 is connected, K of G would be 1. And because G2 is disconnected, K of G2 would be 2. Now, if U and V are two vertices that belong to different components of a graph G, then obviously they're not going to be adjacent, right? Like, if this guy lives here and this guy lives here, since these guys are disconnected, there's no way that these guys are adjacent. There's no way they share an edge. I mean, this is pretty trivial intuition, but like saying it out loud is useful. Like sometimes, like there's some stuff that is baked into the word that we use that we don't really surface necessarily while doing the proof. So it's very important to keep it in mind. It's trivial, but it's something that you need to like bring out of the word in order to use in proofs. There's also this notion of graph distance, which we won't really be using much, but as with many mathematical structures, it may be useful to define some notion of distance for graphs. So for example, you guys know about like the Kevin Bacon distance, right? So the Kevin Bacon distance is like, if you grab two actors, then you find like the shortest distance in the graph of like all actors are the vertices and like the edges are whether they're worked in a movie together. And then you find the shortest distance in that graph, the shortest path in terms of edges that connects a given actor to like Kevin Bacon. So that's actually a measure of like graph distance, the Bacon distance. We can define all sorts, but typically graph distance functions are sort of like, if we have two vertices in a connected graph G, then the distance from U to V is the length of the shortest UV path in G. And the Kevin Bacon graph, it's just like, it's this distance function applied to like having a graph where you have like vertices that the actors and edges are like whether they work in a movie together or not. There's also this idea of like, I think an Euler number. So an Euler number is like, there's a mathematician. No, wait, what? No, it's not the Euler number. Oh, dang it. Who is it? This is a similar notion for a mathematician. I don't know why I can't remember it now. Wow. Yeah, Euler was the bridge guy. Exactly. We're gonna get to the bridge and the guy. Wow, I'm blanking so hard. Monster guy. No, not Lagrange. Dang it. I should know this. I'm such a disgrace. He's the guy that did amphetamines. He's the guy that just like literally did crank in order to do math. Let me see, mathematician amphetamines. Literally what on Google. Paul Erdos number. There we go. Yeah, so Erdos, amazing super galaxy brain mathematician. He literally did amphetamines, aka meth, basically, in order to work on math for longer, which is kind of insane. And there's a quote where a friend convinced Paul Erdos to quit amphetamines for a month. And it's a challenge, right? It's like, oh, Paul, you're such an addict. And Paul quit amphetamines for a month. So he proved his friend wrong. But then Paul said, The only thing you've done is set back the course of mathematics for 1 month. He's a pretty hard dude. Anyway, so history aside, there's also this notion of bipartite graphs. So a connected graph G in figure 12.7 has the property that its vertex set can be partitioned into 2 subsets, U and W. So you see here, we have U at the top and W at the bottom, in such a way that every path connecting 2 vertices of U or 2 vertices of W has even length, and every path connecting a vertex of U and a vertex of W has odd length. In particular, the distance between 2 vertices of U or of W is even, and the distance between a vertex of U and a vertex of W is. Graphs with these properties are of special interest. Does anyone remember? I already showed a graph like this. Can someone tell me where? Does anyone remember where? It's actually at the very beginning when I was modeling that situation between like the jobs and the people. And I said, hey, this is like kind of an interesting graph. And you can imagine like, just like there's many situations that are isomorphic to this situation. Or similar to the situation, there's probably many graphs that are useful like this then. And this is an example. These are bipartite graphs. So the idea of a bipartite graph is that it's a graph that has this structure in which you have every edge of the graph will connect vertices from these 2 sets that we find. So there's not an edge essentially that connects these 2 or connects these 2 or connects these 2 or these 2 or these 2. Those don't exist. And this is, again, pretty useful for various modeling situations. And again, look, every path that connects 2 vertices of U has an even distance. But if we connect if we connect U and W, like in the blue path, then that's an odd distance. So this is, I guess, one of the places in which distance comes in handy. But the notion of bipartite graph for modeling is actually pretty useful too. So if we have a bipartite graph, we can partition the vertex set into 2 subsets U and W, and we call those partite sets. So at every edge of G joins a vertex of U and a vertex of W. So this is essentially what we were just saying. So for example, these are 2 cases of graphs that are actually bipartite, because we can say, hey, we can do it like this. Yeah, like this. So these are my 2 sets, and the same here. So this bipartite nature also has to do with graph coloring. So there's a relationship there. And graph coloring is a very important problem in computer science also. But you can see here, these are the same graphs, or rather, these are graph pictures of isomorphic graphs, the same graph in a sense. And you can see that we can color them, and we can very clearly surface this bipartite structure by arranging them vertically in this manner. Okay. So both of these, we have P5 and the cycle C6, they're bipartite. There's no partition of the vertex set of C3 that satisfies the requirement. Blah, blah, blah. I guess one thing to note here is that C3, C5, and K4 bipartite contain odd cycles. So Coin says, anyway, we can move to the next part. I think I want to go a little bit fast here because I do want to take a break at some point. So bipartite graphs. So again, there's this theorem that is pretty useful for bipartite graphs, and I don't think I'm going to prove all of it, just in the interest of time, and also because I think part of it is kind of ugly, but at least one part of it is pretty cool, and kind of helps you again establish that you can look at a picture, you can develop some intuition with a picture, and kind of motivate a proof. So let's look at this. We're going to prove the left to right direction of the implication, right? Because this is an if and only if. So if you remember from the beginning of class, if and only if means that we need to prove both sides, both ways of the implication, that if this is bipartite, then G does not contain a knot cycle, and if G does not contain a knot cycle, then it is bipartite. So we're going to go one direction. So first, we assume that G is a bipartite graph, because it's like, again, we assume if this, then that. So we assume this, and we assume that it's bipartite and say that C is a cycle in G. So let's look at because if this says if G does not contain an odd cycle. So if it doesn't contain a cycle, then it definitely doesn't contain an odd cycle. So we're going to look at what happens when it does contain a cycle. Okay. So since G is bipartite, there's a partition of the vertex set of G into two sets U and W, such that every edge of G joins a vertex of U and a vertex of W. This is just the definition of bipartite. Okay. Now let's look at what happens. So suppose that U1 it belongs to one of the sets. Okay. And again, we look at this cycle here. This goes up to UK. Okay. So we look at this cycle, right? This is a cycle, and we want to prove that it is odd. Okay. So if we go back to U1, we go up to UK, and then we go back to U1. Okay. So if we start at U1, we can assume that we're in U. We're either in U or in W, and it doesn't matter. So without loss of generality, we're in one of the two. Now, if we're in U1, then every time we traverse an edge in G, we will end up in the other in W. Because if U1 is in U, then again, a bipartite graph has this property that if I partition it in this way, every edge connects a vertex of U and a vertex of W. So every time I move from this guy, I will end up in W. So necessarily, the next part in my cycle is in W. And then the next part is in U here. So you can already see the writing on the wall. There's no way for me to have a cycle without moving an even number of times, because every time I move from where I am, I end up in the other bipartite set. And in order for me to end back where I am, I have to necessarily traverse in this manner. So you can see in this, so then you conclude the proof in that manner by saying, okay, so if I started at U1 is in U, then the next move in the cycle must be in W, and the next one must be in U, and so on. Now, since if you abstract away all the intermediate spots, U1 to UK, the one immediately before going back to U1, this is an edge of the graph. If this is an edge of the graph, then UK must be in W necessarily. If I connect U1 with UK in a way, then UK must be in W. And so K must be even. And then in order to go back to U1, here, I add another edge, and thus, even again, and thus I have an odd number of edges, and that I have an odd cycle. So you can see it in, sorry, I have an even number, an even number of edges and not a odd cycle. So you can see it in the picture here. So in the picture, if I start here, necessarily every time I move out of the set W into the set U. And then if I want to move back to the set W in any way, I need to take a move. So every time I have a cycle, I necessarily have to like pinball between U and W. And every time I make it back to a vertex in W, I have traversed an even number of edges. That's the intuition. So again, if this didn't make sense right away, like try to look at this later with the slides or in the textbook. This is in the textbook is 12.31. Unless anyone has a salient question about this. Did the intuition make sense as to why this is true? It's easy to get mixed up on this, especially when verbally, for me, certainly it's easy to get mixed up when I read it out loud, because I say like U1 is in U and it's like the same letter. But one is lowercase, one is uppercase. You just can't like verbalize that distinction without saying uppercase U, which gets really complicated and annoying really quickly. Okay, so then there's the other direction. This proof is way nastier, and there's no like complementary intuition to go along with it that is simple to explain in a picture. But anyway, that's just for the proof. So the important part is that a non-trivial graph G is bipartite if and only if G does not contain an odd cycle. And likewise, if G contains an odd cycle, again, because if and only if G contains an odd cycle, then G is not bipartite. Okay, so a little bit more before our break. Connectedness in complements. So here we have a couple graphs and their complements. So here we have one graph and its complement, another graph and its complement. And we notice that this graph is connected and its complement is connected. And here we have another graph that is connected, but its complement is disconnected. You see here, we have two components. We have a bunch of components, actually. This component and this component and this component. So a natural question then is, can a graph and its complement both be disconnected at the same time? So we know that we can have both of them be connected and one of them be connected and the other disconnected. But can both of them be disconnected? So turns out the answer is no. If either of them is disconnected, then the other one must be connected. So if G is a disconnected graph, then the complement of G complement is, or G bar, let's say G bar, just to be shorter, then G bar is connected. So this has a proof, and the proof is actually pretty nice and fairly intuitive. So let G be a disconnected graph. Then G must contain two or more components because it's disconnected, right? Obviously, so it follows. G must contain two or more components. So then to verify that G is connected, to verify that, we must show that for every two vertices U and V of G bar, there is a UV path in G bar. So this is G bar, but it could also be U because they share the same vertices. So what this is saying is like, hey, this is disconnected, right? So we want to show that for every two vertices here, there is a path in this complement graph. That is what we want to do. Okay, so we have two cases. Let's suppose that U and V, the two vertices, belong to different components of G. Right? They can either both belong to the same component or different components. If they belong to different components of G, then U and V are not adjacent in G because they're in different components. And this is the notion that I highlighted earlier, remember? That it's implicit in this idea of disconnected, but it's so obvious that sometimes we don't surface it explicitly. So here we're surfacing it explicitly. Since they're in different components, they cannot be adjacent. They cannot share an edge. Otherwise, the components would be connected. And so U and V are adjacent in G complement. If they're not adjacent in G, then they must be adjacent in G complement because G complement just grabs everything that is not adjacent in G and makes it adjacent. So then there's clearly a UV path of length 1 in G, exactly of length 1. So that's pretty nice. Case 2. Let's suppose that U and V belong to the same component of G. So for example, here we have U and we have V, let's say. These are the two components, the two vertices on the same component. Now let W be a vertex of G that belongs to a component different from the one containing U and V, like this one. This is in a different component, right? So therefore, W is not adjacent to either U or V in G. It is not adjacent to U, and it is not adjacent to, but in this case, in this picture, U is not adjacent to X, and X is not adjacent to C. But then there must be a path from U to X in the complement, because if they're not adjacent here, then they're adjacent in the complement. And likewise, there must be a path from X to C in the complement, because they're not adjacent here. So you see, the complement traces a nice path of length 2. And that's it. So again, let W be a vertex of G that belongs to a component different from the one containing U and V. Therefore, W is not adjacent to either U or V in G, which implies that W is adjacent to both U and V in G complement. Consequently, UWV is a UV path of length 2 in G complement. So this is a picture. And I think this is a nice picture. It kind of, again, shows you how you can like draw these pictures and kind of get an intuition as to why this is true. Okay, so now degree and connectedness. If G is a graph of order n, such that the degree of V is greater than or equal to n minus 1 over 2 for every vertex of G, then G is connected. This is just like, so basically, if you can verify, so wait, the graph is just a picture. So like these, so I guess I should have made this explicit. These letters don't necessarily correspond to these letters. These are just I understand now that it's kind of unfortunate. I wasn't like thinking about putting this in like saying like this is like the one we saw in the previous slide. So this is not one that I made for this. So yeah, so if we want to make it nice, and I can maybe fix this for the slide so that like the labels correspond to this. The important part is the picture. So if we go here, then if we have W as a vertex of G, U and V, so we would label it like this. This is U, this is V, and this is W. This is W, this is V, this is U. Okay. All right. Okay, so if we can like show that a graph has this lower bound on all of its degrees, then we can guarantee that it's connected. So it's not every graph, it's a particular type of graph. So for example, in the graph in the picture, which is, I think, the one from before, that is certainly the case. Because if you look at all these, if you look at like, this is an order 6 graph, right? So n minus 1 over 2, that is 2.5. So we need that every vertex has degree more than 2.5, and every vertex has degree 4. So that's definitely true. Okay. So this graph works for this theorem, qualifies. Okay. So how can we prove this? Let G be a graph of order n such that the degree of V is greater than n minus 1 over 2 for every vertex V of G. So this is just saying, let this be true, right? Just assuming that the conditions for the theorem hold. To verify that G is connected, we show that there is a path between every 2 vertices of G, because that's what it means for a graph to be connected, that there's a path between every 2 vertices of G. Like X and Y be 2 vertices of G. Okay, so let's check it out. We want to show that there is thus an XY path. Of course, if X is adjacent to Y, then XY is an edge of G, and thus G contains the XY path XY. So if they're adjacent, then duh, we're done, right? So let's look at let's look at what happens if they're not adjacent. Let's assume that they're not adjacent. Okay, since they're not adjacent, and since the degree of x is greater than or equal to n minus 1 over 2, and so and the same goes for the degree of y, again, because of our assumption, then each of x and y has a set at least n minus 1 over 2 neighbors, right? So this is saying, hey, if the degree of these guys is greater than, in the case of the picture, if the degree of these guys is greater than 2.5 at least, then they have at least more than 2.5 neighbors, right? And you can't have half neighbor, right? So in this case, it would be 3 or more. But that's like what you can be guaranteed. And again, they don't have a neighbor in common. They don't have a neighbor in common, right? They don't have a neighbor, rather, they're not adjacent to each other. It's not they don't have a neighbor in common. They're not adjacent to each other. So x is not a neighbor of y, and y is not a neighbor of x. But if there is no vertex of G that is a neighbor of both of them, then this is what happens. If you grab the neighborhood of x and you add x to it, and the neighborhood of y and you add y to it, then these are now disjoint sets. Meaning, if there is no vertex of G that connects x and y directly, if there's no like guy between x and y, then necessarily the set of all the neighbors of x and the set of all the neighbors of y, and you include y and you include x, they're disjoint. Okay, because these guys are definitely not neighbors to each other. And if they don't contain at least one guy that is a common neighbor, then their neighbor sets, they must be disjoint. And each of these sets has cardinality n plus 1 over 2, at least, because we know that the neighborhood has n minus 1 over 2, at least, and then you add 1, which means you add 2 over 2. Now you have same denominator, so it's n minus 1 plus 2 over 2. So that is n plus 1 over 2. Okay? Okay, but now think about what this means in terms of like these two things. So I'm saying, again, in my picture, I have x and I have y, and I'm saying that there is nothing here in the middle that connects them. So now I have the neighborhood of x, the neighborhood of y, they're disjoint, there's nothing here connecting them. And this guy has, if I add x to the neighborhood, I got this set has n plus 1 over 2. This set has n plus 1 over 2. They're disjoint. So then the cardinality of the sum of these, of the union of these two, is the sum of their cardinalities. If I grab n plus 1 over 2 plus n plus 1 over 2, I get n plus 1. But that's a problem because the graph itself has order n. So if I get n plus 1, I'm saying that there's parts of the graph that add up to n plus 1 vertices, but the graph itself has n elements, right? It says this implies that the order of G is at least n plus 1. However, this is impossible since G only has n vertices. Therefore, there must be a vertex C that is a neighbor of both x and y. So this says that xc to y is an xy path in G, right? So we just shown that if I don't have this common link, and I grab their neighborhoods and I add x and I add y to them, then I get enough elements to surpass the order of the graph, which is impossible. And that was if they didn't have this common element. So they must have this common element in their neighborhood. And thus there's a path from here to here. And that's the proof. Okay, last concept here. Did this make sense? Should I go over this again? Okay, so I guess not. All right, let's look at this now, bridges. An edge E in a graph G is called a bridge of G if G minus E. So this is G, take away that edge, has more components than G, more components. That means, again, remember the number of components is the number of like connected partitions of G, right? So a vertex V in a non-trivial graph G is a cut vertex of G if G minus V, if I take away that vertex, has more components than G. So essentially, bridges and cut vertices are like either edges or vertices that I can remove from a graph to make it disconnected. So in this picture, if I take away the edge TU, then I have this component and I have this component. It's disconnected now. It's pretty intuitive, I think. Likewise, if I take away the edge R, the vertex R, then now I have this component, and then these guys are going to be their own components floating around. This is a pretty useful notion. In particular, for a connected graph G, an edge E of G is a bridge of G if G minus E is disconnected, while a vertex V of G is a cut vertex of G if G minus V is disconnected. In fact, if E equals UV is a bridge in a connection graph G, then G minus E always has exactly two components. So if we cut a bridge, we get exactly two components every time. As we saw in the vertex example I just gave, the cut vertex, that's not true for vertices. In that case, we cut R and we got three components, not two. So the following two theorems presented without proof provide characterizations of bridges and cut vertices in a graph. An edge E of a graph G is a bridge of G if and only if E lies on no cycle of G. So if E lies on a cycle, then it cannot be a graph. A bridge. And if E is an edge, then it can lie on no cycle. And the converse is the contrapositives are also true. A vertex V of a connected graph G is a cut vertex of G if and only if there exist vertices U and V, U and W distinct from V, such that V lies on every UV path of G. Okay, so what this is saying is that for something to be a cut vertex, then it needs to be a mediator between other vertices, between every path connecting other vertices in each component. So if this is part of if this is in one of the components I would get from cutting R, and this is part of a component I would get from cutting R also, a different one, then every path that connects these two must go through R. Because think about it, if it wasn't true, then that would mean that I would have another path that doesn't pass through R that connects them. But then if I cut R, then I will have a path that connects them anyway, and they're not disconnected quite yet. Okay, and let's do one problem that I think you'll find pretty useful, and then we'll have a quick break, and then we'll go over as much as we can of 12.3, which might not be much. Let G be a connected graph such that for any x in the edge set with x smaller than k, the graph G minus x is connected. Suppose, so this is saying that if I take out k edges, less than k edges from the graph, then I still get a connected graph. So the minimum number of edges that I can take out is k in order to get a disconnected graph. Now suppose that E sub k is a set of edges of k edges, so that cardinality is k, such that G minus EK, so if I take out those edges from the graph, I do get a disconnected graph. Prove that for any B in the set of edges, any edge in the set of edges, E sub k, is actually a bridge of this thing, of G, take away everything in E sub k except that bridge, that edge. So the first line tells us that the smallest number of edges we must remove to disconnect G is k. That is what it's saying, hey, if I take away less than k edges, then I'm still connected. Now, obviously, if I grab E sub k, which has cardinality k by definition, and I subtract v, one edge from it, then I have k minus 1 edges in this new E sub k minus v set of edges. So then necessarily, if I take away this set, E sub k minus v, this set from G, I'm taking away k minus 1 edges. And I need at least k edges to potentially ever get a disconnected graph. So if I take that away from G and I call it H, I call the result H, H must be connected because I haven't taken away k edges. I took away k minus 1 edges. So then the question that becomes, is B a bridge of this set here, which is the one that we're asking about? And the answer is yes, because if you note, we know that H is connected. So then we say, okay, if V is a bridge of H, then whenever I take away V, if I take away V, then H needs to become disconnected, or the result needs to be disconnected. Okay, so suppose I take away V. So here I have G. H is equal to this. We already said it, so I expand it. And I'm saying, okay, I have G, and I take away everything in E sub k except V. But then I also take away V. So if I take away everything in E sub k except B, but then I also take away V, in total, I've taken away everything in E sub k. But here I said that G minus E sub k, if I take away everything in E sub k from G, then I get something disconnected. So this is disconnected. So H minus V is disconnected, which in turn means that B must be a bridge of H, because it's the one thing that if I take it out of H, I make it disconnected. So that's what I say. As first, I subtract everything in E sub k except B, and then I also subtract B. So in the end, I subtracted all of E sub k. And since G minus E sub k is disconnected, then H minus V is disconnected. So since H is connected and subtracting B makes it disconnected, then B must be a bridge. And that's it for now. Okay, so we don't have that long. We might actually, I might have to run over in terms of time. If I do, you guys feel free to leave at 9:30. You guys feel free to leave whenever, frankly. The lecture might have to be a little bit over, just a few minutes probably. But let me stop sharing my screen. Did I stop sharing? Oh, I didn't quit my presentation. That's what's going on. So let's take a 10-minute break, okay, guys? So we convene at, actually, let's take, okay, yeah, we come back in like 10 minutes. So 9:38-ish, 8:38, sorry. Right. You guys can see my cat right there. Four minutes of break left. Any feedback I can get, guys? Am I going too quick, too in-depth, not in-depth enough? Is this making sense? The last theorem was a bit tricky. The one with bridges. Yeah. I think it's tricky in part because I did it in a general case. I didn't say what K was, and that's on purpose because if I did it in the non-general case, then it would be a too strong a hint for something you may be doing in the future. I'll open next slides. Any other bits of feedback in case I do this again? I guess you can tell me a recitation or in person as well. All right. Got 1 minute and then we'll pick up again and hopefully this one will go faster. It is less content. So a lot less content. So hopefully we can wrap up by 9. What do you guys think of this topic? Give me some reacts in the chat, regardless of my presentation. Do you think this is more fun working with like the pictures and so on? Thing with the homework, there's 2 isomorphisms, and I think those are pretty fun. There's a couple that are more like proofs. One is similar to something that we've already done here. And we're definitely going to be doing a lot of practice in recitation as well. So you get some more experience with how to actually solve some of these problems. I know that section 12.1 especially is just words, but it's kind of important to have that vocabulary in place. All right, let's keep going. Okay. So now we're actually going to talk about the Königsberg bridge problem. So I think someone mentioned it already, and I accidentally mentioned this guy Euler, because I was looking for Euler's number, and I said Euler's number, which is just E, which is nothing to do with that. You guys know what E is. So can we find a way to walk through every bridge exactly once in this picture? This picture corresponds to the Königsberg Bridge. This was Königsberg was a city in Prussia. Now it's part of Russia. You know how things change. And there's this mathematician, Leonhard Euler, who wanted to solve this popular question that people had in Königsberg at the time or something. And it's like, well, can we actually find a way to walk through every bridge exactly once? So he said, let me take a stab at it and, I don't know, invent all of, well, not all of graph theory, but like, you know, invent graph theory in the process. So it turns out that we can use graphs, if it wasn't obvious by now, to understand this problem. So we can represent it using a multigraph. We haven't worked with multigraphs so far, and we won't really work with multigraphs that much, but a multigraph essentially has multiple edges joining nodes. It can have multiple edges joining nodes. So then if we think about it, like if we want to create, if we represent the pieces of land in between bridges as nodes and the bridges as edges, for example, if there's a way to go from B to D, have an edge, then the question becomes, is there a trail containing every edge of G? Can we somehow traverse this graph such that we cross every bridge exactly once? Again, a trail was a walk with no repeated edges. Okay. And again, remember that we said that the degree of a vertex was the number of neighbors. In terms of multigraphs, we actually want to use a slightly different definition, which is actually better definition, which is the number of edges incident with a particular vertex. That way we can account for multiple edges. Okay, so now we're introduce this notion of Eulerian trails. So suppose that G is a connected graph, meaning there's no like floating parts. Then an open trail that contains every edge of G is called an Eulerian trail, while a circuit that contains every edge of G is an Eulerian circuit. So this is pretty simple. Basically, if you can find a trail, meaning a walk with no repeated edges, that happens to contain every edge of G, then there you go. You found an Eulerian trail. Now, if you furthermore find that that thing is a circuit, meaning it ends up back where it started, then that's an Eulerian circuit. And if it has an Eulerian circuit, then the whole thing is called Eulerian. So here we have an example. So here, if we follow this sequence, then we'll actually touch each edge exactly once. So we can do S1 to T1, T1 to B1, B1 to X1, X1 to Y1, Y1 to C1, C1 to X1, X1 to W1, W1 to U1, U1 to B1, B1 to W1, W1 to T1, T1 to U1, U1 to S1. So we painted the whole thing. If you played like The Legend of Zelda, there's many puzzles throughout the Legend of Zelda series that essentially amount to Eulerian trails, which is pretty cool. A lot of like tile painting puzzles and like Orgo Seas and Orgo Ages. You play those games. So this is actually pretty useful. It's pretty useful to think about this stuff, whether you're solving puzzles, whether you're asking questions about bridges, or whether you're doing serious computer science. So then again, this question, the equivalent question is, does the multigraph corresponding to the bridge contain an Eulerian circuit or an Eulerian trail? And we're actually not going to solve that, but we're just going to keep talking about Eulerian graphs. So there are a bunch of useful theorems for this. One of them is that if G is an Eulerian graph, then every vertex of G is even. Every vertex of G is even. There's an intuition for this, and it's like essentially that you're coming in and out. That's one way to think about it. So let's look at that a little bit in a little bit more depth. So let G be an Eulerian graph. That means that G will contain an Eulerian circuit that starts at x0 and ends at x0. Now, if V is a vertex of G that is not the initial vertex of C, meaning some of these guys, and therefore it's not either the first or the last one, then each time that V is encountered on C, it is both entered and exited, and therefore contributes 2 to the degree of V. This is exactly what I just said, right? Consequently, the V is even, has an even degree. And if V is the initial and terminal vertex of C, then C contributes 1 to the degree of both of V, both as the initial vertex and as a terminal vertex. So if we look at these guys, then each of them will contribute 2 edges. And if we look at these, if he happens to be looking at this one, then we contribute 1 here and then 1 here. So in turn, we contribute 2. We contribute 2 to the degree here. Okay, so because we contribute when we get to the end and when we start from the beginning. So thus V is even here as well. So whether we're looking at the degrees in between the path or the beginning and the end, each of them will have even degree. Yeah, that's basically the idea. That's the intuition and the proof. Okay, so let G be a non-trivial connected graph. If every vertex of G is even, then G is Eulerian. So this is the other way. And this one I'm not gonna cover because I don't have time. And I think it would take me a lot of time. But you should read it by yourself. This is actually one of the few times that we've provided you with a proof by algorithm. So this is what it calls a constructed proof. We're showing that there's an algorithm that finds what we want. Meaning, if we know that every vertex of G is even, then we can construct an algorithm that will, there's an algorithm that will construct the Eulerian path. So it's a proof by algorithm. And you should check it out. It's actually pretty intuitive if you actually read it in detail and you draw it. But I don't want to spend too much time on that because we're already a little bit late. Okay, so let's look at these two theorems. Theorem 12.40 says that if G is an Eulerian graph, then every vertex of G is even. And 12.41 says that if every vertex of G is even, then G is an Eulerian graph. So if we put these two together, what do we get? I don't have the chat. I should probably have the chat. Where's the chat? Yeah, I can't see the chat. Oh, yes, if and only if. Good job. Yeah, good job, Andy. Exactly right. We get if and only if, because we get in one direction, and then here we have in the other direction. So we get that if G is Eulerian, that G is Eulerian if and only if the vertex of G is every vertex of G is even. So this is pretty useful. There's other implications that are also pretty useful. One of them is that if G is a connected graph and G has an Eulerian, where's the pen go? Laser pointer. Then G has an Eulerian trail if and only if G has exactly 2 odd vertices. Furthermore, any Eulerian trail of G begins at one of the odd vertices and ends at the other. So this you can think about this in terms of like the proof that we looked at it earlier. Like if G has an Eulerian, if G has exactly 2 odd vertices, then you can actually find an Eulerian trail because everything in the middle, if you look at the proof that we had here, right? It was like everything in the middle had even degree, and these guys had odd degree. They had degree 1 and 1, and they were the ones at the extremes. So it turns out that it's actually this if and only if, a really strong condition in consequence of these Eulerian graphs. And these two things are useful because they allow us to quickly identify whether things are Eulerian circuits or trails or not. So for example, if I give you these 9 graphs, can we like very quickly identify which ones have Eulerian graphs or not? I mean, if we were to do it by actually looking for the circuits or the trails ourselves manually, then we would definitely run over, right? So I introduced this because I want to like clock out at 9 and then go watch Succession. So this is going to make it really convenient for me. So let's start ruling out which one can absolutely not have an Eulerian circuit or trail. Which one of these are you sure that cannot have an Eulerian circuit or trail? Okay, so G9 definitely cannot. Good job, Andy. And that's because, well, G9 is like not even a connected graph, right? It's disconnected. So if the Eulerian trail needs to traverse every edge, then we cannot traverse every edge because we cannot get from here to here. That's why every single theorem that we've had prefaces it by saying that G is connected. So this one's ruled out. Okay, so then we can look at the ones that have only, well, I guess I just spoiled it. The ones that have only even vertices, like these. This one is a regular graph. And each of the vertices has degree 4. We already saw this graph. So they all have degree 4. So therefore, this one is, they exist in an Eulerian circuit. In this one, likewise, all of the ones in here have degree 4 or 2 in G6. So this is also even. And then let's look at the ones to our left. The ones to our left, so Andy, you said G2. So in G2, it actually does work because we only have 2 odd vertices. So if you look at these guys, these have degree 2, degree 2, degree 2, degree 2, but these guys have degree 3, degree 3. So there's only 2 odd vertices. And you can like very readily find the path, right? Like you can do like tuk, 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 tuk. Wait, no, not like that. Like this, tuk, 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 tuk. Boom. Oh, I might, when I draw, does it not show until the end? Because I think if so, that's making it problematic. When I draw, does it like show continuously when I do the pen or when I do the highlighter? I think with the highlighter, it might not. And I just realized that. We can do just so we can see, we can do like this, 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 like this. Okay, and the same goes for the other ones. The other ones, each of them only has 2 vertices with odd degree. Here's one, and here's the other for this one. And for G8, it is this guy and this guy. Notice that this is not, there's no connection here. And the same goes for this guy. I think. Okay. And next slide. Wait, G5. Am I dumb? 2 odd vertices. What? Oh, duh. Yeah, I'm dumb. Sorry, guys. This guy has 3, and this guy has 3. Boom. Yeah. Anyway, so yeah, so these are all the ones. And you can see this is pretty, this very easily allows you to like check and rule them out. And lastly, we're going to talk about graph operators, and then I think we can actually finish in time. Cool. So we have 2 graph operators. One of them we kind of already discussed. So the union G union H of 2 graphs G and H with disjoint vertex sets. Disjoint vertex sets. This is the important part. Is that graph whose vertex set is the union of their vertex sets and whose edge set is the union of their edge sets. So the interesting part here is that the union of the two graphs H and H is always disconnected, and the number of components is the sum of the components. So this makes sense because if you think about it, like if this is G and this is H, right? These are, in order for the vertex sets to be disjoint, then the vertices in G cannot appear in the vertices of H. So then when you do their union, when you put them together into one single thing, there cannot possibly be an edge from one to the other, because the edges of this guy are disjoint from the edges of this guy in the respective graphs. And then the next one says the join G plus H of two graphs G and H with disjoint vertex sets is that graph constructed from G and H by adding all edges joining the vertices of G and the vertices of H. So the join of two graphs, connected or not, is always connected by construction, because you always add the edges that connect vertices of H and vertices of G and H. So by construction, it will always be connected. Because if you have, say that this is G and this is H, then we're going to add edges from here all the way there and from here all the way there to get this. So necessarily, we will get something that's connected. Oh, wow, that's it. I think I had more stuff, but I guess not. So that's it, guys. Is there any other topics that you guys want me to cover in this last 5 minutes? Any questions, anything before you all just click log out? All right. Well, hopefully this was helpful. We are going to discuss more of this in recitation. I will look at I will put the recording tomorrow, probably. I don't think I'm going to upload it today. It's a little bit late.